I'm Steve McDowell, founder and chief analyst at NAND Research, and I'm here today with Val Bercovici. Val has a great title. Val is Chief AI Officer at WEKA. Now, if you don't know WEKA is one of the leading innovators in high-performance, massively scalable data infrastructure. They provide the data backbone for some of the largest media and entertainment, HPC, and AI clusters in the world. I mean, one thing you say about WEKA is they know data. Which leads us to today's topic, which is, what else? AI, and more specifically, how storage and data infrastructure is evolving and must evolve to meet the demands of generative AI. This is a critical topic as generative AI moves from a small set of players developing foundation models right into the enterprise, where it's fast becoming a business critical function. So thanks for being here, Val.
A real pleasure, Steve. I can't wait to get into this topic.
Oh, me too. So before we start nerding out on storage, and I know we're going to, I want to talk about how we should think about the economics of AI, because, at the end of the day, AI is really all about creating business value. And WEKA was very early in talking about and thinking about how data infrastructure needs to evolve to deliver that value. You were very early on, start talking about something called tokenomics. Explain it like I'm five. What is tokenomics?
Sure. I mean, the one way to explain it, which we won't do today, is to sort of delve into the spreadsheet accounting aspects of it all, or even like the various incentives of the different layers of delivering a token to you. I think a better way today is to just take a look at really relevant headlines. Cursor, probably the most popular AI app today, if you measure it by a revenue basis, I believe they're reported to have about $500 million in annual recurring revenue after less than 2 years. Faster growth to revenue than even OpenAI themselves, which used to be the fastest. So as the killer app of AI, Cursor is now having to rate limit and throttle their top tier users that were on unlimited token plans because Cursor's own internal costs for tokens from the underlying model providers, such as Anthropic Claude and OpenAI and Gemini and so forth, are now too high when the volume of tokens is too big. So we're seeing end user revolt, so to speak, by not getting what they were promised from their agent provider, coding agent provider like Cursor. Anthropic themselves, with their really popular Claude coding agent service, clearly with preferential tokenomics or input token pricing and output token pricing from the underlying Sonnet and Opus models themselves, they were just forced to impose throttling and rate limits because even with their own internal preferential pricing, this notion now of agent swarms, which are at least about a dozen agents in parallel solving a particular coding task, they are now consuming more tokens than Anthropic has supply for. And so it's really all coming down to how can people afford as many tokens as these latest generation apps are consuming.
So Val, let's take it down one notch and make it more concrete. Who cares about tokenomics? Who's paying the price of the things that we're talking about? And it sounds like there might be multiple audiences.
Yeah, there's about 3 to 4 layers depending on how we want to count them here, Steve. So I'd say the base layer are the GPU hosters. So that would be either the hyperscalers or this really massive new category in the industry called an AI or a neo cloud that NVIDIA is wisely spraying out GPU allocation to. And they're provisioning, they're getting the energy contracts, they're buying the real estate, they're literally hosting the GPUs. And the business model there is to rent the GPUs out on an hourly basis. Their primary tenants are the model providers, so the OpenAIs of the world and the Anthropics of the world, and the open weights model hosters such as Together AI and others that host DeepSeek and other Llama open source models. They are the ones that actually show the pricing even more transparently at the dollars per input token, dollars per output token, and now dollars per cached input token level. As we get closer to the user, though, developers pay those token prices, and developers are developing apps like Cursor, for example, or Manus AI, or other popular agents that are on the market right now. Those agents are paying the model providers those token costs, but they have to make some gross margin as well. And they have to make that really difficult transition from a unit cost with unit economics to flat monthly pricing tiers of $20 a month, or interestingly enough, $200 a month. That's not even enough for a lot of developers on the market today. And many developers are getting multiple $200 a month plans just to get the token allocations they need. And then ultimately it's us, the end users, right? Are we comfortable paying $20 a month, $100, $200? There have been reports, as you might have seen, of OpenAI considering domain-specific, vertical industry-specific, $20,000 a month agents that leverage this entire stack I mentioned optimally and deliver PhD Nobel laureate class outputs and results per domain and vertical. So that's the spectrum we're looking at today.
So just to level set, when we talk about tokens, these are kind of the basic units that flow in and out of generative AI words, right?
Correct. I mean, the conversion, I think, loosely is one word to about, or three-quarters of a word to about one token. And that varies with multimodal. So if you're looking at audio, video, the token units are different. But think of it as, yeah, the common currency of AI is ultimately this common unit, the token. And it's a thing that gets converted to 20,000 dimension vector in some cases inside this working memory we're going to dive into called the key value cache, which takes something that's hundreds of kilobytes in size and makes it gigabytes in size in memory and puts a lot of pressure on these GPU clusters and GPU servers because, quite frankly, they just don't have the memory needed to serve out all of these tokens.
All right, well, help me out here. So I understand as an AI consumer, right, how tokens influences what I'm spending, right? You talked about Anthropic and others there. But if I'm a practitioner and I'm delivering these AI services, right, and I care about tokenomics, maybe from my enterprise perspective, because maybe I have my own infrastructure, or maybe I'm a service provider. I guess cutting to the chase, right? What does tokens have to do with storage and data platforms? Draw the line for me.
So this is interesting because it's somewhat existential, and let me explain what I mean by that. On the surface, when you're doing inference, particularly for enterprise AI apps, you're trying to ask questions about canonically, a PDF document, or perhaps a code base, or a whole library of content, which could include videos and PowerPoints and certainly PDFs and so forth. And so you're doing something called retrieval augmented generation, where you're pre-computing these vectors in a process called embedding them into a vector database. And then when you actually do the query, the prompts against that content, you are retrieving that content from that vector database as part of that retrieval and retrieval augmented generation. And that all, is very storage intensive, but it's also something that the ecosystem, particularly vector databases, are designed to, quite frankly, minimize the impact of storage on. So like most databases, they try and optimize and abstract away the need for premium high performance storage and work very well over commodity storage. And that's why I say that in the world of inference, which is distinct from training, but in the world of AI inference,
Hmm.
and as you know better than I, about 4 out of every $5 of AI now is going to inference, no longer training. In the world of inference, it's really a different conversation. The GPUs themselves work with GPU memory on a GPU and a GPU server. They don't directly touch the storage. So if retrieval augmented generation isn't part of the workload mix, and that's the case in most inference use cases, statistically or proportionally, then how does storage impact, inference? How does storage impact memory? Those are oxymorons, and I think we're going to dive into how the right kind of storage configured the right kind of way can actually deliver memory value for AI inference.
Okay, before we jump into the technical bits, though, are there metrics, are there ways of measuring and forecasting kind of tokenomics at enterprise scale?
I think the most transparent ones that end users don't see as much, but all the app developers, so it's either internal app developers in enterprise implementing these retrieval augmented generation RAG systems with vector databases, or the ISVs, the actual app developers and agent developers, they see these three classes of pricing, which have become somewhat standardized across the industry. The first class of pricing is price per million input tokens. That's often if you're a cost leader in the sense, if you're a value or premium sort of quality leader, it's in the dollars per million input tokens. Then there's the corollary, the output tokens, and that's up to 10 times more expensive because that's ultimately what we care about is the outputs, and we want those to be high quality outputs. And there's a new class of pricing that appeared about 6 months ago commonly called the cached input, in between input and output pricing. And that's now often at a standard of about 75% discount off uncached or regular input token pricing. So a lot of what we're seeing right now, whether it's, rate limits and throttling, or whether it's the actual SaaS monthly price of an agent or a AI app, is determined by those price per million token costs I just mentioned.
And I'm just a storage guy. I don't understand AI really. What's cached versus uncached tokens?
So cache versus uncached refers to the way inference works. We've
Okay.
heard these terms autoregressive or, stochastic parrots, predict the next token basically, randomly, but, as accurately as possible based on the probability of what the next token should be, based on the 1,000, million, or trillion prior tokens. And that prediction actually has to factor in all of those prior tokens. So the larger what's called the context window, meaning the longer your conversation with
Yep.
your LLM has been, or the more content you're asking it to process, the more you have to compute. And that's why, it's really important to understand, what it is that you're processing and where that input token process cost comes from. It's largely a direct function of how big your content is that you're asking questions about and how many questions you're asking. That's called multi-turn on small or large context. And then you have something called a reasoning token with a lot of OpenAI models, for example, and DeepSeek models, and almost every modern LLM introduced. We call them LRM, large reasoning models, in 2025 over the past 6 months or so. So there's a lot of interim processing to get the deep research type of answer or the really sophisticated scientific PhD level answer. And finally, the ratio is often much larger, many more input than output tokens, but then we have the final result, which would be a piece of code or a summary of a long context or the answer to a very sophisticated question. And that's where all these tokens get involved, and they don't map directly to megahertz or gigahertz of a processor.
Right.
They don't even map directly to a very common metric in the AI world called the memory bandwidth utilization, or the model flops, floating point, million floating point operations per second. There's many variables in between that ultimately determine these costs, and it's not rocket science, but you do have to know all these variables and account for them.
It's a whole new way of thinking about my infrastructure. But let's pause on tokenomics for a second and get a little more concrete, and let's talk about storage and data infrastructure and how that might relate to tokenomics, right? So give you kind of a softball to begin with, but it's a good baseline. Why can't I just call up CDW and buy whatever array they have on sale this week? Does traditional storage fail at AI on inferencing and training?
It doesn't fail from a technical perspective. You can plug in traditional storage to your GPU server, but it's kind of like trying to suck a baseball through a straw, or actually a basketball more appropriately through a straw.
Mhm.
It just is not going to work that well, right? So what you want is you want storage that understands what it's being plugged into. And the CPU tends to work sequentially, serially. It processes data and instructions, and then it outputs something, more or less one at a time. And yes, we have multi-core CPUs now, and we have multi-threading. So we're into hundreds of cores, and we're into many, many threads, sometimes per core. So let's be generous and say there's about 1,000 things going on a
Mhm.
modern CPU server today. GPU servers just laugh at that, because any GPU has about 17,000 cores. Now, they're not the same kind of cores, of course. They're much more focused on just arithmetic, matrix multiplications. They used to be called ALUs, arithmetic logic units.
Uh-huh.
So they focus on just that, but there's so many more cores. And the most common servers today, almost universally, don't just have one CPU, one GPU, or two or four GPUs. They have 8 GPUs. So you have 8 by 17,000 cores per server that are hungry for data. And if you're not feeding all of those cores, those 100,000 cores or so, in parallel, you are just choking your server, and you're paying about $250,000 per server. NVIDIA, of course, would prefer to sell you a whole rack unit, something called an NVL 72 of these, 72 GPUs. You're paying between, let's say, $3 million retail for these things. I don't think NVIDIA is discounting much lately. So if you're starving this $3 million capital asset while it's depreciating rapidly, you're fundamentally doing AI infrastructure wrong. You need to feed this at full wire speed.
Okay. Well, there's a couple of ways we can talk about this, right? We could talk about, the technologies that are evolving to support that, like GPU Direct from NVIDIA and some of the work WEKA has done. But maybe before we do that, let's talk about, you talk about starving the GPU, right? And GPU efficiency. Where does storage get involved? Where are the bottlenecks that I can address with my data infrastructure, right? And I'm sure there's different answers for training and inference.
Yeah.
But how do you look at that?
Let's start with a couple simple ones for training. So training is comprised of these cadence cycles in a cadence called an epoch, which is multiple experiments. And the way you formalize these experiments is you record checkpoints. So very often, in fact, nothing really matters until a checkpoint is persisted somewhere, typically on storage. So the amount of data in memory involved here can be on the order of terabytes of memory for these modern high-end models. If you can't get terabytes of memory down to persistent storage, and what happens quite commonly in these large GPU clusters is a GPU fails, or more than one GPU fails, and you lose that portion of the memory. You've now lost, a ton of work by some extremely expensive researchers now that are, if you read the latest headlines, can charge up to $200 million in their compensation packages, right? There's one example of 300 million. So it's very important to persist this work literally as quickly as possible on the order of seconds, not minutes or hours, to minimize the chance of losing one of these checkpoints and losing the results of this training. So checkpointing is really critical, shortening the epoch so you can quite frankly bring your models to market faster. And implicit in that is not just saving them, but of course loading them to test them. And we'll talk about inference, loading them more than once, loading these models as quickly during training and inference. And we call that the verb we use inside WEKA is fire hosing, because we want to just burst all of these models into the GPU memory as fast as possible, have the GPUs process them, and where necessary, fire hose all that data back down from the GPUs to the storage layer.
So that covers training, but as we bring AI into the enterprise, right, into the business, it's much more about inference. There's not a lot of enterprises training their own foundation models. So where are the bottlenecks within those workflows?
The bottlenecks tend to be at both scale and efficiency, and maybe a parallel looking back about 10 or 15 years. When we first started doing hyperscale web services, it was more of an art than science to be able to load balance thousands and millions of HTTP requests across a web server like Nginx and so forth. And then we figured it out. Then it became a commodity scientific thing. We're kind of at that early stage with LLM inference right now to load balance, many, many user sessions across many GPUs is A, not at all the same as doing as a web server over CPUs. And B, there's just, the logic is literally probabilistic versus deterministic. So there's a lot more going on in terms of how to match the right GPU with the next token it needs to predict with a slice or at least a copy of the working memory it needs in order to do that. So inference serving at scale involves actually not a traditional network, but it involves this high performance compute network, which is many terabits per second, not just hundreds of gigabits per second.
Mm.
And it involves a lot of pre-positioning of what we call key value transfers, KV cache transfers between GPUs and between servers, so that as a token is routed to a particular GPU, it has the working memory to predict, the next set of tokens and so forth. So it's quite intricate, it's quite involved, and the level of stress it would put on a storage system would break a traditional storage system, which is why storage has to evolve to the compute network to add value at inference time.
Here's where I get a little lost, and I want you to help me out, right? Because again, my background, enterprise IT storage, I understand that, right? I know how to do storage for a database, for an email server, whatever. But you're talking about especially when you start talking about things like KV cache, right? I understand the concept of I have data, it's maybe vectorized, I need to serve it to my GPU and fill that context window, right? Storage typically doesn't get involved in caching data used within the processing of AI. And you're saying that, well, with AI and inference and KV cache, maybe it does, right? So can you expand on that just a little bit? What does my storage infrastructure have to do with KV cache and a GPU?
I'm glad you asked because it's definitely non-intuitive. So one of the fundamental bottlenecks independent of storage at inference time is inference is actually broken down into two phases. The first phase is itself very GPU, very compute intensive, and that's something called the prefill phase. So we talked about this earlier. It's taking your tokenized input prompt, whether it's your own question, whether it's the content you're talking about, or both, and converting that into key vectors and value vectors. And that is really adding many thousands of dimensions to it and expanding, really mushrooming out the size from hundreds of kilobytes to many, many tens of gigabytes of memory, quite frankly, which needs to fit either in the GPU high bandwidth memory or at least on the GPU server that the GPUs are connected to, the DIMMs, the DRAM. What we find, just the reality today, is that loading a common model like DeepSeek and loading those model weights fills up most of that GPU and server memory before you've even taken your first prompt. And these prompts, again, are not trivial in size. They're quite substantial in size when you convert them to the working memory of the LLM, the KV cache, which has to fit next to the weights. So before you know it, you're just frankly out of memory. After you've done all this initial pre-fill phase one computing to begin to actually decode the prompt and generate the output tokens or even the reasoning tokens before the output tokens, you're just flat out of memory. So memory is the bottleneck for inference. And the lithography and manufacturing for either high bandwidth memory or DRAM is not keeping up with the progress of the GPUs themselves. So every year when NVIDIA and AMD and others generate these impressive new GPUs and deliver more millions of flops per second and so forth, they're not proportionally delivering as much of an increase in the working memory. So actually with every generation, memory, which began as a bottleneck, increases as a bottleneck for this process. And there's a desperate need to provision more memory that the GPU can work with. And the role that storage can fit, if it's flexible enough to work in this configuration, is to sit on the compute network. So when storage both sits on the compute network, and those are often called the east-west ports on a GPU server. There's often 8 of them, and they're at 400 gigabits to an 800 gigabits per port, unidirectional. That contrasts with the north-south network, which is often a front-end or storage network. You often see 16 times, 1/6 times the number of bandwidth and PCI lanes, quite frankly, on the compute network. So if a storage system, quote unquote, can attach over that compute network that's 16 times faster, if it can saturate 16 times more the bandwidth, it delivers DRAM DIMM class memory performance. And the inference servers that are balancing the model weights and balancing the KV cache, the software like VLLM, for example, or NVIDIA's Triton TRT LLM, they know how to use both kinds of memory. They know how to use high bandwidth memory on the GPUs, server memory as finite as it is on the motherboard, or this KV cache memory over the compute network, regardless of what the media is on the other side of that compute network. And often, again, with WEKA, that media is a DRAM class media. The inference server, serving DeepSeek and all the other Llama popular models, they know what to do with that. And they now see 1,000 times more working memory than before, which radically changes their performance and radically changes those tokenomics we spoke about.
So as you were describing it, I'm trying to map it back to classical computing, right? Which is, in a classical system, when an operating system needs more memory and I've used up all my memory, I page it out to disk. My disk doesn't have to be aware of that. It doesn't have to do anything special. It's just attached, right? In the scenario that you're talking about where I'm doing KV cache extension, and I think WEKA has a solution you call augmented memory grid for that, does the storage system have to be aware that it's a repository and an extension for KV cache? Do you have to do different engineering to build that?
You don't re-engineer, with WEKA at least, you don't re-engineer the storage system. You configure it differently.
Okay.
Configuring, we have a new brand, a new name for our storage system called Neural Mesh, which I think is very eponymous. It really is a mesh of containerized microservices. If you can configure your storage system, data path, control path, management plane, microservices to function correctly over that compute network with that enormous bandwidth and nearly saturate that bandwidth, then that configuration alone ends up appearing as memory to the software that runs on the GPUs, and that would be this inference server software like VLLM, for example. That really is kind of the magic. Is it's just configuring, and there's a particular protocol involved. It's an RDMA protocol called GPU Direct Storage, which we often abbreviate to just GDS. When you configure that GDS protocol over that compute network, that is the magic combination that unlocks memory class performance out of NVMe devices at 10 or 20 times lower cost and about 1,000 times more density, unlocks that memory class performance and value.
All right. And we should point out GPU Direct is an NVIDIA technology based on their Mellanox RDMA cards, right? So, about one of the things that distinguishes WEKA from more traditional storage architectures is you take a very disaggregated approach. And you talked about Neuromesh a second ago. What's the value of taking a disaggregated approach to this problem versus, more traditional storage?
Right. I think it's taking full advantage of the fact that we now have this technology called non-volatile memory extension technology, which is a core protocol to our SSDs. You really want to treat it as extended memory versus storage. So that's one thing that WEKA does natively. The other is that fundamental realization that in HPC networks, the network is faster than the motherboard. This is profound, and most people don't internalize this. So WEKA's access from the motherboard over more PCI lanes on these high-performance compute networks is what enables a disaggregated mesh to deliver more performance than is constrained, ironically, by the motherboard itself. Virtually every other storage system on the market, even modern scale-out ones, even some that call themselves disaggregated, still have this client-server controller architecture, or a controller and a controller motherboard, and what happens to be on that motherboard is the bottleneck. And the mesh fundamentally has no inherent bottleneck like that. It's a many-to-many configuration. And when a mesh has a many-to-many set of connections, it delivers that full performance in a disaggregated, you can also call it decentralized manner, across all of the resources available to it. And when these happen to be on a on a supercomputer network, that's a substantial amount of resources to leverage.
Fair enough. But I raise it because, as we record this, we're coming out of conference season, and I'm not going to name check competitors except to say it's every storage company, right? Whether it's Pure, NetApp, Dell, Lenovo, to a person, they all support GPU Direct in some way, shape, or form, but they bolt that on to kind of a traditional NAS offering. How do you look at this differently than more traditional enterprise storage companies, right? Beyond just the interconnect, how should we think about our data infrastructure for AI?
Well, just like the token pricing we talked about
Hmm.
earlier on, you don't just pay what you feel the token should cost. You pay the quantitative hard number of what the token costs. So this is actually aside from a very hyperbole driven marketing industry, on the storage side alone. It's not a qualitative discussion; it's a quantitative discussion. So you need to be able to function, particularly in any kind of optimal inference scenario over the compute network. You need to be able to leverage 16 times more bandwidth than traditional storage systems, which is not a trivial task. And you need to be able to deliver the actual kind of latency that a server, any piece of software, expects out of memory. If it's thinking, it's talking to memory, and you have variable latency that's somewhere between 3 and 5 milliseconds, the software will just time out and panic in some cases. That's just not memory latency. On the other hand, what's also deceiving is on paper, people think that memory latency has to be in the nanoseconds. And DRAM DIMMs, of course, are. But as the software, as this inference server software like VLLM particularly, or even Triton TR-TLLM from NVIDIA, as that software is accessing the DRAM, for example, on an NVIDIA DGX or Dell HGX motherboard, that is actually microsecond, hundreds of microseconds of latency. So that's the specific tolerance window under which these systems have to perform to deliver this level of value. And it's on the order of low hundreds of microseconds. And again, that's something that statistically, numerically, factually, objectively, only WEKA operates, and only WEKA has published objective benchmarks showing that we have random I/O returning, reads and writes on the order of hundreds of microseconds versus many milliseconds.
Let's circle back. Let's bring it back to the business value, right? We started with tokenomics. Let's kind of wrap with tokenomics. There's been a lot of recent innovation, much of it driven by work at WEKA that you've just talked about around optimizing data infrastructure to deliver higher value AI, if you will. You talked about augmented memory grid. You talk about neural mesh. So my question is, what emerging infrastructure technologies do you believe will be game changers as we look at the next wave of AI?
Quite frankly, Jensen says this himself during all of his keynotes, is the network is faster than the server now in an AI factory, in a high-performance computing supercluster, an NVIDIA supercluster. So I would say evolution instead of even revolution here, because the revolution was understanding you're dealing with a GPU instead of a CPU and configuring your whole stack, whether it's the storage, the networking, obviously the servers, your energy for that matter, energy density. Once you get past that revolution, now we're into really fundamental evolution, where as we speak, we're seeing now the appearance of the GB300s, the Grace Blackwell 300 GPUs and servers from NVIDIA. Those come with these network adapters, these 800 gigabit unidirectional per port, so 1.6 terabyte bidirectional per port network adapters, the CX-8s. There are 8 of those on the CPU network. So now we're talking about, I believe, 6.4 terabits, or double that if you do bidirectional of bandwidth, that is clearly available to anything that can connect to it. And you want next generation infrastructure that can connect to that can fully leverage that, and cannot leave those giant capital allocations of your GPUs and your energy and everything else, your data centers, idle, that are fully utilizing that by maximizing the compute in phase 1 of inference, for example, and the memory in phase 2 of inference. And more importantly, delivering great latency to your users, not imposing rate limits or throttling your users, because now your internal OpEx is way lower and you've got the gross margin, you've got the ability even to compete with price leaders like DeepSeek and Kimi K2 and others.
We're in very early days of bringing AI to the enterprise, right? And you're talking about fairly robust systems for initial needs. These are just going to scale over time. And I think it's important to note for enterprise AI workloads, these are not static workloads, right? I've always got data coming in. There's processing I need to do, clean up on data, whether it's streaming data coming in or data from databases. I got to vectorize it. It's a continuous loop, right? It's not, I optimize for inference and I've done my diligence. I have to support my whole data strategy for an enterprise with AI as one output, right? So do you think about, when you're designing your storage systems, do you think about kind of holistically what that data lifecycle looks like that ultimately leads to AI and inferencing?
Yeah, NVIDIA likes to call that the data flywheel, which I think
Mhm.
is a very appropriate term. We very much think, within that data flywheel because, if we go back to the training part of our conversation, you've got to be able to prep the data, and the data doesn't come in just one giant multi-terabyte file. It comes in billions and trillions of small files of different types and sizes, and you've got to process them, as you said, you've got to label them, then you've got to be able to actually transform them into one of these epochs and see if the loss function is good or not. Often the first time you do that, it's bad. Often the thousandth time you do that, it's better. So just the training part of that, flywheel alone is quite intensive. And then you flip into this whole other mode of inference. And sometimes you do fine tuning in between. And
Mhm.
by the time you've done a lot of inference, you realize, hey, there's so many common patterns here that I want to update my model so it runs more efficiently. And you've begun a brand new cycle of that flywheel. So we actually, from a storage perspective, have an internal expression inside WEKA. We call that the IO blender, because there's so many different types of IOs, large, small, reads, writes, small block, unstructured, structured. And unless you have a system that takes them all at face value and knows how to optimize globally across, exabytes, frankly, of data for minimum latency on each and every SSD, NVMe device as we see them across that exabyte of data, and always look at the queue depths for everyone, every device, and always look for where the latency starts to become too large, and make sure that we don't saturate the latency of any device. That is a tall task, but that's ultimately what we do. And And this becomes more and more relevant to this flywheel because I don't know if you checked, Steve, but these are multi-dozen, $100 billion flywheels soon, approaching commonly trillion-dollar flywheels. And so, yeah, getting this right is the difference between profit and loss at an unprecedented scale, quite
Yeah,
frankly.
it's not getting any less expensive. From everything we've talked about, kind of my high level takeaway here is, AI, especially AI at scale, forces us to think differently about storage and data infrastructure. And this is not just technology; it's about the very economics of AI and the return on investment for our enterprise AI efforts. I'll give you the last word. Are those the right takeaways? What should we leave? What should we leave our viewers with?
Yeah, if we're just gonna use a really popular cliche in tech, is it's the Steve Jobs think differently, right?
Yeah,
AI and GPU computing, not just supercomputer computing from the past that's based on tens of thousands of CPUs, but supercomputing with GPUs is the most parallel thing that computer science has ever done. And that requires fundamentally different infrastructure up and down the stack at the silicon level, at the rack level, at the energy level, at the software level. So understanding the differences here is important, and staying, on the leading edge of it to make sure that you're actually cash flow positive versus cash flow
right.
negative so that you don't have to impose rate limits and throttling to your end users. It's a delicate dance, but it can also be a fun one if you know what you're doing and you're working with the right ecosystem.
Awesome. This is a perfect place to stop. If our viewers want more information, go to weka.io, where there's a wealth of detailed technical blogs and other resources, including a paper that NAND Research wrote with WEKA that goes deeper into the bottlenecks and the challenges of delivering data and to enterprise AI. So thank you for tuning in. Thank you, Val, for a great discussion.
Really enjoyed it, Steve. Really looking forward to the next one too.
Awesome.